Hello, my name is Kimberly Tay.
And my name is Christine Yu.
And for our project, we engineered a novel device known as a microbial fuel cell that could produce clean energy and help clean up oil pollution. Now, we first got interested in this project around 2 years ago. And at that time, I was interning at the National Oceanic and Atmospheric Administration doing oceanic research. And I specifically saw how incidents like the BP oil spill caused high amounts of oceanic pollution that was very harmful to the environment. And the cleanup methods to remove this pollution was invasive and very expensive. This made me want to look at more sustainable and eco-friendly methods. And since I had prior experience with microbial fuel cells, which can produce energy and have some wastewater treatment capabilities, I thought it could also be used to help clean up oil spills.
And I have previous experience with environmental pollutants because I interned at SUNY Old Westbury for 2 years. So we merged interests and we continue our research at the Manhasset Science Research Department.
So we logged in about over 1,500 hours doing our research, and for our project, again, we use a device known as a microbial fuel cell, and we basically call it mud power. And what happens is it uses naturally occurring bacteria in organic sediment in wastewater or polluted sediment to produce energy. And what happens is this naturally occurring bacteria, as they metabolize and break down organic materials like oil, they release electrons, and the microbial fuel cell collects these electrons to produce energy. And at the same time, it can help speed up the natural oil degradation process as well.
And we used a loofah sponge, which is really common in Asian culture. You can eat it and also used to clean your bodies with. And it's really common, and we use that as a cheaper alternative to commercially used materials. And we found that the loofah sponge is 26 times more cost effective and also produces 3 times greater power density than commercially used materials. And we found that our microbial fuel cell degraded 93% of the oil in our sample.
So we basically developed a cost-effective and more sustainable alternative to oil spill cleanup and clean energy production.
Basically killing 2 birds with 1 stone. And we would like to thank the Manhasset Science Research Department for allowing us to conduct our independent study. And we would also like to thank our teachers, Ms. Allison Hanger and Mr. Peter Guastella, for their guidance throughout the entire process. Thank you.
Rheological characterization of attapulgite nanoclay modified cement slurries for oil well cementing applications. My name is Augusta Wamanzuna, and this summer I conducted an oil well cementing project. Now you might ask, why cement? For me, it was because I wanted to get rid of the misconception that I had that cement was simply just rocks and water. But starting 3 years ago, I learned that it was in fact very much more complex and accounts for up to 7% of human-caused carbon dioxide emissions. Now, using this as inspiration, I have conducted research in this field for 3 years now, and it has culminated in an oil well cementing project. My goal conducting this research was to mitigate the causes of the 2010 Gulf oil spill, which was very disastrous. I chose to add attapulgite nanoclays into the cement in order to enhance this property called thixotropy. Thixotropy is pretty much the dual property of a material behaving like a liquid and a solid. Cement should behave like a liquid, pretty much flow like water when it's entering an oil well. However, when it gets to the bottom, it should develop enough gel strength to resist the overbalance of pressure that is characteristic of an oil well setting. By adding these clays, this property of thixotropy was enhanced and calls for testing of the cement in an actual oil well situation. Now, I know that cement is not just rocks and water. I conducted research at Columbia University under Dr. Shiho Kawashima, and my research teacher is Ms. Michelle Flannery.
A close family member of mine was diagnosed with an eating disorder when she was in college, and thankfully she was able to overcome the illness, but so many people are not as fortunate and they're not able to overcome mental illnesses, and that was what inspired me to conduct this research and to look at the genetic and the underlying causes of these mental illnesses that are affecting so many people around the world. Hello, my name is Rachel Mashal. 2 years ago, I presented my work on eating disorders and anxiety at the International Conference on Eating Disorders in Boston. And after that experience, I really wanted to look at the underlying genetic and biochemical aspects that control these mental illnesses. And that was what led me to my project that I conducted this past summer. And this project was looking at how genetics and diet can influence propensity for addiction, as well as protection against overdose in fruit flies. So I manipulated the genetics of my fruit flies, so I used 3 different strains of flies that had different levels of TOR signaling, which is signaling in the target of rapamycin, a nutrient sensing pathway. And I also manipulated the diet of my flies, so some were on high protein, low protein, and normal protein diets. And then they were given 3 different levels of caffeine. And what I was looking to see is how the different combinations of genetics, diet, and the amount of caffeine that they were on would influence their propensity for the addiction. That included their ability to climb during withdrawal, as well as their drug-seeking behavior, and how it would influence their ability to withstand a toxic dose of the drug, so ability to overcome a fatal overdose. The results of my study found that lowered protein intake protected the flies against addiction and toxicity. So a dietary restriction or lowered protein intake caused the flies to seek out the drug less and to climb better during a locomotor task, and it also allowed them to live longer while on a fatal dose of the drug. I was lucky enough to work at LIU Post under the guidance of Dr. Ted Brummel. He was such an amazing mentor, and I'm so lucky that I was able to work with him this past summer. And I was guided by Mrs. Barbie Frank, my research teacher, and she really helped me throughout the entire research process.
Hi, my name is Jessica Huang, and what motivated me to do this project was ultimately looking at my older brother, who I'm convinced is a genius, looking at people like Steve Jobs, who can innovate and problem solve so readily. I was kind of inspired and curious as to what makes one person smarter than another, what makes one person capable of innovating and reasoning so readily. For 2 summers, I've been looking at fluid intelligence, which is abstractly defined as the ability to reason through new problems. And what I wanted to look towards is what properties of the brain make one person more fluidly intelligent than another person. So specifically, if you attempt to represent the brain as a network, so a network composed of points and connections between those points, so brain regions and interactions between those brain regions, you can quantify with mathematics the properties of this network, and then you can use correlations to evaluate a correlation between brain properties and fluid intelligence test scores, and we can see which brain properties index fluid intelligence and define fluid intelligence and our ability to reason. I'd really like to thank my mentor, Dr. R. Todd Constable, for accepting me into his lab for 2 summers now, and providing me with so much guidance and equipment for pursuing this project of fluid intelligence. And I'd also like to thank my science research teacher, Dr. Serena McCalla, for guiding me this entire way.